Hello everyone, this is the final project demonstration of group 13. This is the progress demo 4. So in this project we went through ray tracing, and what ray tracing is. Ray tracing is basically a rendering method that simulates the way of light interact with object to create a highly realistic image. So in our project we use this for a radio wave data collection using ray tracing. We created an environment using Blender, and then we rendered and collected all the radio waves with the help of ray tracing. So after that, I created a uh, machine learning model sorry, machine learning model which predicts the geolocation of a person, which is like the X, Y, and Z axis from the three axis point APs, radio waves. The input are RSSI 1, RSSI AP1, RSSI AP2, RSSI AP3, and the output is the geolocation of the person, which is the X, Y, and Z coordinates. The data set which we manually collected using the ray tracing and simulation, and we created nearly 1 million data point. And then the feature extraction was, we made input feature as RSSI AP1, RSSI AP2, RSSI AP3, and the output labels were the XYZ geolocations. Then we split the data in like 80 and 20, which was 80 for training and 20 for testing using train test split. And then we scaled the feature using standard scaler to improve the model performance. The model architecture was like, there was an input layer which had the three input features, RSI values. Then they have like multiple dense layer, batch normalization, dropout to prevent overfitting. Then the residual connection to model's performance. And then the final output, which outputs three values X, Y, and Z, representing the geolocation. And then I created a custom accuracy model, uh, which measures the Euclidean distance between the predicted and the actual coordinates, and it has a threshold of less than 1, distance less than 1. If the threshold is correct, then that particular point is considered as a correct, as an accurate prediction of XYZ coordinates. So this was the loss and accuracy graph. As you can see, we have the gradiently decreasing loss, which is good for us, and at the same time the accuracy was increasing, which is again a good sign for us. So the model was trained using the Adam optimizer, and it has a learning rate of 0.001, and we used mean squared error as a loss function. The training was done for 10 epoch with a batch size of 64, and the validation split was of 20%. We we trained this and gained an absolutely good accuracy of 99.79%, which indicates an excellent prediction in performance for geolocation task. So we used mean square error, which indicates high accuracy, and test accuracy with a threshold of unit 1 was 99.79%. So that's it from the model training part. So before choosing that model, I tested with some other models as well, which didn't give me a good result. So at first I tested with a simple linear regression model, and it gave me a very bad mean square error. Then I tested with the polynomial regression. Again, it gave me a pretty bad result as compared to my other thing. Then I made a decision tree, uh, and it gave me, it also didn't give me a very good result. Then I tested it with random forest, and again the result was good with compared to other. So I went ahead and tested it with SVM and KNN, before proceeding with my actual model. So again, the mean square error was significantly good compared to other models. Then after that, I created a machine learning model using TensorFlow, and I imported the data as a CSV file, all the three RSSI values and the XYZ values to predict. The uh, Then I split the X and Y in 80 into 80% and 20% ratio, 80 to 20 ratio, my bad, sorry. Then I use standard scalar and fit the model. Then I defined the architecture. As you can see, it has a input function. Then it has a multiple of dense layers, which dense layer batch normalization dropout to prevent overfitting. And then I added this model. So this was the model architecture. Then I used the Adam optimizer with a learning rate of 0.001 and loss function as mean squared error. Then I trained the model. So this was the thing. Model has a total parameter of 666,000, and trainable parameter was 662,000, with non-trainable parameter being 3,840. So I trained the model for 10 epochs, and then I got a validation accuracy of 99.79% and the custom accuracy of 99.16%. So, and then I tested it with some value if I'm getting a correct value or not. So as you can see, it gave me a pretty good result. So then I plotted a couple of graphs. As you can see, I plotted the training and validation loss. Then after that I plotted the training and validation accuracy graph, and then I went ahead and plotted the model using the plot model API from Keras. So this was the model which was there. So as you can see, if I go down, and the output of 3, which denotes XYZ factors. If I scroll up, and you see, this is the shortcut part and the input part of 3, X, Y, and Z. Sorry, RSSI AP1, AP2, and AP3. So this was all from machine learning part aspect, and later on we'll continue with other part of the project till now. Thank you.
Hello guys, welcome again. So this week, um, I as usual I worked on the ray tracing. So this week I actually worked on I wrote a program of my own right to basically do my very own ray tracing. So instead of relying on external libraries that MATLAB offers, so I wrote everything in Scratch so that it might become novel and it becomes more powerful. So I will show you the code. So this is the code. So here I again similarly I read from a MTL file. So this MTL file will contain the material details. The OBJ file contains the dimension of the model, the 3D model. So I will run and show this to you. So here, but basically what I do is, yes. So this is the 3D model, and this is my RSSI distribution, combined RSSI distribution for our simulated case. So actually, this took pretty much about 3 to 4 days for me to land, make this code work. I actually started to work on another MATLAB code too, which is much more sophisticated than this. But that I will save for another video because that's a work in progress. This time, what I did here in this code is, here basically I ray traced. So how did I ray trace in this case? Because so I assuming a transmitter. Okay, so if you have a transmitter, uh, I basically take the model, I import the model, right? And in short, I basically for every face and for every face, I basically assume a reflection point. Okay, and I calculate that reflection point too uh, 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 based on planar geometry, right? So for every phase, if you have a transmitter and receiver, actually let me go to that part of code. uh, yes, so for each base and vertex, so this is the function calculate reflections. So this is where I calculate the reflection loss based on the material properties too. So uh, let me be simple. So first, I will check whether there is a line of sight that exists between the transmitter and the receiver. Uh, so other than the line of sight power, I also add the reflective power. Okay, how many reflections? The number of reflections depends on the number of faces for the 3D model. So if there are six faces, there would be six reflections. So this is overarchingly simplistic because in a practical RF transmitter, the rays coming out of a practical RF transmitter, there might be multitude of reflections. But here I wanted to do everything from scratch. So this is relatively a very simplistic model, but this nevertheless is close to it's not very far from realism. So but it involved a lot of geometric calculations such as these, and calculating the reflective power. And for every reflected ray, there it loses some energy due to its it basically imparts some energy to the wall, to the concrete wall, to the face to which it lands. So essentially, first to calculate reflection, I basically use this vector geometry to basically calculate the reflection point. The reflection point would be typically be uh, at the center of the projection of the transmitter and receiver coordinate. Okay, and that would be the reflection point. And then so I have to calculate the path loss for that reflected ray, and also the energy that the ray lost due to interaction with the wall. So I have to calculate two things. So I calculated those, and finally, here I didn't assume a diffractionless medium. So but just a multitude of reflections, the number of reflections equal the number of faces of that 3D model. So that is what I assumed. And obviously there are some phases where uh, I assumed a steel shoe rack, okay, in some position. So that also is accounted as a phase. So that also I included, and every phase has some permittivity associated with it. So that will affect the loss due to reflection. Correct. So these are all the points that I wrote. So this is the snippet that calculates that. So calculate reflection loss, right? So this reflection loss coefficient is basically used in the loss equation, and this loss is basically added to the overall loss along with the path loss, free space path loss that I calculated. And then I added one major, very very important part, which is basically calculating path loss based on region. If it is at near field, then this particular equation is obeyed. If it is a Because typically the d squared law is obeyed only at far field. If not, um, that equation is disobeyed. Okay, it is not. It is violated. That condition is violated. So I specifically added snippets so that near field condition is taken into account. And finally, the rest is pretty much similar to the old code with some uh, nitty gritty modifications. So this is what I did. And finally, also used ray triangle intersection. This is uh, so this uses this Moller Trumbour algorithm. So this is an additional algorithm that is used for basically categorizing the 3D model as triangles. So but in essence, this is what I did, and thus finally we obtain the path loss. So I also obtained the results here. So let me try opening it. Yeah. So this is how the path loss result is stored. Okay. So yeah. So you might have also seen the heat map that was generated due to this. So data. So this is a mimic of a realistic scenario. Okay. But in the next video, I would basically I'm actually working towards a model, working towards a simulator, my very own simulator that essentially is very close to realistic propagation scenarios, and outputs a CSV file that is basically like taking a proper measurement. Okay, that is what I wanted to replace, right? So, and then with the power of ML, if you could leverage that, we could basically estimate prediction, estimate the position of a particular target based on their signal vector, based on their Wi-Fi fingerprint, uh, without physically measuring that particular location. Just by giving the map, the ML model should be able to correlate the map with the RSSI vector. So that's our ultimate aim. So that is what we are progressing towards. So yeah. So this is this week's progress. I actually worked on one another MATLAB code, which is haphazard. So I would save that for the next video. So, but yeah, so this is what my part was. So I wrote this entire code by myself to basically simulate a near realistic wireless race propagation. Okay. The propagation is based on the number of phases that it interacts with, and there would be a reflectivity loss associated with it. Uh, and finally, some path loss would be basically free space path loss plus the loss due to reflection and stuff. The other the other mechanism why it took so time, the other reason why this the generation of the output of this code took so time for me to write is because three dimensional, because the now I'm doing 3D localization. Just due to the addition of the third dimension, things get even more complicated because there would be a blow up in the number of reflections now in the other dimension too. So that needs to be taken into account. But the next code that I'm working on, it also takes into account diffraction and refraction. So it would be much more complicated, and then three dimension it's going to be very sophisticated. So yeah, so I'm looking forward to that code. I'm on progress working on that code. Meanwhile, Mayank and Sharvesh, they would I hope they would in the previous video they, as well as in this video, they would show their updates too. So yeah, thank you.
Hello all. So now we look into the update for the final project. For this week, we have improved the ray tracing model, and then we have discussed how our ML models work in our project. So now we'll look into the improvements in the app part. So what we have done is we have incorporated the AWS functionality within our app. So we have written a separate class to send data. It's named here called AWS Data Center. In this, we have added functionalities to perform streaming of data from our mobile device to the AWS system that we have. For that, we have integrated this AWS Data Center class with our main activity.java file. So here we specify the endpoint and the API key needed, and then we start and stop streaming of our data. We have also incorporated it to work for three-dimensional data. We started with two-dimensional data, and then we have reached a point of three-dimensional data, and it also saves the positions as a backup. After that, we are streaming the data to AWS as well. So to test our application, we performed a few postman requests After performing postman request by using basic form data, we have a basic output for the time being. After sending the postman request to our system, we have received coordinates of the, sorry, not the coordinates, the RSSI values that we had sent. So those are being printed here. So this concludes the update with respect to the mobile apps for this progress video. Thank you so much.